what we have done so far, given a K, we came up with one possible clustering arrangement around these randomly chosen red points. Okay, but this is not the end of the clustering. What we do next is so once you draw this green line based on the distances that we computed, we take the average of all the data points that are belonging to one cluster. Okay, so you are trying to move your red point to a better location. So essentially what we are saying is once you assign all these data points to a red point that we have chosen randomly in the initial phase, once I get this green circle, I am going to compute the average of all these data points. Okay, and then that average will obviously be somewhere kind of in the middle of all this, right? Let's say that average is here. Okay, so my cluster center has moved from here to here. Okay, and similarly I compute the average of all these data points, and then I'll get a cluster center here. Okay, so now we have two new cluster centers. So I go back again. These are the new cluster centers I have, and then I repeat my process. Okay, that means given these two red points, I compute the distance between the black point and the red points and then assign it to the closest cluster, essentially organizing the data into clusters, okay, or into segments or groups, such that within the cluster there's a lot of intra-cluster similarity. Okay, so if I place multiple data points into one cluster, the similarity between those 2 points is very, very high. Okay, that means they are very close to each other, and therefore they are put into the same segment or same cluster. Like if purchasing behavior of two of my customers are very similar, then I will put both of them into the same market segment. Okay, so there is a high intra-cluster similarity. Okay, at the same time there is a low inter-cluster similarity. Okay, if I have customers from two different segments, their purchasing behavior should be as different as possible, right? If that is also same, then there's no point in putting both of them in different clusters or different segments, right? So the goal of clustering is to organize data into clusters such that there's a high intra-cluster similarity, that means within the cluster, and then there's a low inter-cluster similarity, that means between the clusters. Okay, and we need to find groupings or clustering in order to account for those restrictions of high intra-cluster and low inter-cluster. Okay, the third point is simply finding the natural groupings among objects. Okay, like for example, if I have data points like this, okay, if this is my data, a bunch of points, a natural grouping is obviously this is one cluster and this is one cluster, right? Because they are kind of close to each other. So that's why it's kind of informally, that's what you're trying to do. You're trying to find the groupings that you normally do just by looking at them. Okay, does that make sense? Good. Okay, let's go. So Ashish says, can you please tell what is a typical problem statement in clustering? Identify into clusters or further optimization. So the problem statement can be just to find market segments in my customer base. That itself can be a problem statement. Or it can be something else for which you find clusters and then build on top of that. Okay, like in order to answer that, let me give you another example. In any store like Walmart or Macy's or any store, you have a lot of promotions, right? Sales. Now, how do they figure out which item to put on sale? And even if they determine this item should go on sale, what is the percentage discount that they should give? Okay, and typically they give something like in the first week of promotion period they give you 10% discount, and after a week they give you 20% discount, and after 2 weeks they give you 30% discount, just to make that item go away from their shelves. Okay, so and typically you can't do this kind of analysis, meaning figuring out that particular schedule, right? Like first 1 week should be 10%, second 1 week should be 20%, and so on. So that's kind of called as a schedule or a markdown schedule. Okay, figuring out that particular schedule for every item in your store is impractical and may not be useful also. Like Walmart has millions of items or thousands of items, so you can't come up with that schedule for every single item. Okay, so typically what they do is they kind of categorize all your products into different categories and then analyze individual categories one by one. Okay, so that's kind of making your problem of finding the markdown schedules for all your products little easier by finding out some clusters within your product portfolio. Okay, and the clusters can be like all the items that have similar sales profile will go into one cluster, or all the items that that are targeted at a particular set of customers will go into one cluster. That can be whatever the store manager decides, but essentially you are dividing your products into different clusters and then trying to figure out a markdown schedule for individual clusters. Okay, so here the end goal is to figure out the markdown schedules, but you are relying on the clusters in order to get to that that thing. Okay, so the problem scenario, the problem statement need not always be saying, okay, find the groupings. Okay, it can be something else, but you start with the groupings and then build on top of it. Does it make sense, Ashish? Okay. And yeah, so we already talked about a bunch of things here. Why clustering? Organizing data into clusters to show the internal structure that is present in the data or the internal groups. Okay, and sometimes, as we just discussed, partitioning itself is a goal, like finding the segments in your customer base, or prepare for some other machine learning techniques like summarizing the news, or in this case finding out the markdown schedules. And discovery in data is simply just to understand the data. Okay, just to see how the data is there, like as an exploration. You can use clustering as well. Okay, and there are multiple types of clustering algorithms, not just multiple techniques of solving a clustering problem, but there's also multiple types of what clustering is, or what the goal of clustering is. So one is exclusive clustering. That means it's like a partitioning. You're dividing all your data points into partitions so that every data point belongs to a single cluster or single partition. Okay, there's no overlap. Whereas in the other case, this one, overlapping clustering, a single data point can belong to multiple clusters. Okay, so it's not really partitioning in a hard manner, but you are allowing for these multi-membership cluster. Okay, so typically this is called as a hard clustering. So you're partitioning so that one data point belongs to one cluster, and the overlapping clustering is also called as fuzzy clustering or a soft clustering. Okay, where you can have multi-membership. And this can also be useful depending on the application. Like if I want to, one popular example is if I have all the users of Twitter and I want to group them based on their interests, okay? Then one person can be interested both in sports as well as politics. So that person should belong to both the sports cluster as well as politics cluster, okay? So there the multi-membership kind of makes sense, okay? And there may be other applications where exclusive clustering makes more sense than overlapping clustering, okay? So depending on the application, you figure out which one to use, okay? And there's also something called as hierarchical clustering, which is typically done in a, obviously, as the name suggests, it's done in a hierarchical manner, okay? So actually, let me take one example, and that should give you better understanding. One classic example for that is something called as a phylogenetic tree, okay? Something like this, which is like an evolutionary tree, okay? This evolutionary tree essentially connects all the organisms in the world, in the planet, and trying to, so it's like we always hear that humans and chimpanzees are close to each other, right? They're kind of coming from the same ancestor. And if you like draw this entire evolutionary diagram, even humans are similar to frogs, or humans are related to dinosaurs and so many other organisms in certain manner, right? So the way that evolutionary tree looks like is something called as hierarchical clustering. So here in this particular example, in this particular picture, we are grouping all the dinosaurs, different species of dinosaurs, right? So imagine this tree to be upside down, just to understand even in a nicer way. At one level, you are kind of combining these three into one grouping, okay? And then you are connecting that group with other species. Then you get this group. And then you combine this group with other species, you get this group. So you are going step by step in constructing these groupings, okay? And that's why it's called hierarchical. And at any point, you can kind of draw your line and say, okay, these are the groups I can look for, these are the things that I want to focus on, and so on, okay? And typically, when you do hierarchical clustering, you construct something called as a dendrogram, which looks like this. So at lowest level, every one of your data point is an individual cluster, and then you hierarchically kind of merge individual data points to become a cluster, and then that cluster is merged with some other data point to become another cluster, and so on. And you keep going up and up and up by grouping more and more data points, okay? Since you go in this hierarchical manner, it's called hierarchical clustering, okay? So as you can see, this is different from the partitions that we constructed, something like here, right? Here we simply say all of these data points belong to one cluster, all of these data points belong to one cluster. There's no hierarchy here. Whereas here there's a hierarchy. And depending on the application, this may be more useful than this kind of partitioning kind of approach. Okay? Does that make sense? Any questions? So everyone understood the type of clustering: hard clustering, soft clustering, and hierarchical clustering. Okay, so actually before we proceed, should we just take a break, 10 minutes, and then we'll resume, and then we'll look at the k-means algorithm and other things. Okay, so it's 7:58 for me, and let's meet again at 8:08. Okay, do we have Naveen? Naveen is here. Naveen Das. Yes, Sudhir. Naveen is here. Okay, Murali says, suggestion, whenever you expect feedback or in break after, if you let us talk instead of typing it, it would be more interactive because I'm not. Oh, excellent. Definitely, Murali, if you want to speak, as I mentioned in the first class, please let me know. I'll unmute you and you can speak. So this applies to everyone who feels talking is better than typing long sentences. Absolutely. Just let me know and I'll unmute you and you can ask your question or share your thoughts or whatever. Okay, so yeah, let's meet again in 10 minutes. Is everyone back? So Murali, do you have any specific question that you would like to ask? If you are there. Okay. Any questions before we proceed? So should we go into the rest of the class? Okay. Okay, all this particular slide says there's no one answer to any clustering. There can be multiple arrangements of the data that kind of satisfies your requirements or constraints. So it really depends on whether a particular solution is sufficient for you or not. Okay? And okay. So in this slide, we said clustering is something where you organize your data points into clusters or groups or segments such that there's a high intra-cluster similarity and low inter-cluster similarity, right? We are okay with that definition. However, the subtle point is that the notion of similarity, okay? In order to say there is high intra-cluster similarity, first I need to define what is similarity, right? I need to, for a bunch of data points, I need to define a similarity metric that is applicable over those data points. And depending on the data, the type of the similarity measure or the type of the distance measure, which is the opposite of similarity, can change. Okay, and in order to do, before we execute any clustering algorithm, the first and foremost thing that we agree upon is the distance measure or the similarity measure that needs to be used. Okay, and there are many formulations of distance measure or the similarity measure. Okay. And depending on the application, you use one over the other. And in a lot of cases, you don't even know what to use. So you just try a bunch of things and see which one kind of gives you nice results. Okay. And as we just said, similarity and the distance are kind of opposite to each other, right? Distance, or also called as dissimilarity, are kind of two faces of the same coin. Okay. And for any clustering algorithm, you either need a similarity measure or a dissimilarity measure, one or the other. And these measures reflects the degree of closeness or separation between data points. Okay, that's clear, right, to everyone? Like in our market segmentation example, in order to say the two customers have the same or a similar purchase behavior, I need to mathematically quantify that similarity between their purchase profiles, right? And that's exactly what this notion of similarity measurement. Is that clear to everyone? Once we have such a notion, then we can obviously say whether the clustering mechanism method has high intra-cluster and low inter-cluster and so on. Okay, and as we just said, similarity measures. Similarity measures the degree to which a pair of objects are alike or similar. Okay, and yeah. So essentially says similarity as matching according to which patterns are seen as different viewpoints, possible instantiations are. So yeah, you can go through the slide, but all it says is there are multiple types of similarity depending on the underlying data. Okay, and there are well-known distance measures that are typically used in many applications, but you can devise your own distance measure for your data set. That's totally possible, and many people do that because only you know more about the data, and therefore only you know how to capture the similarity or the dissimilarity between two data points. Okay. And the popular distance measures are, one is the Euclidean distance, which is the most popular, and probably all of us know it already, which we learned in high school. Euclidean distance between two data points in the space. And there's something called Manhattan distance. We'll see what that is. And there's also cosine similarity or cosine distance, Tanimoto distance, squared Euclidean distance, and so on. Okay. There are many more, not just these, but these are like popular names that you will see in practice. And Euclidean distance is simply the distance or the length of the line that is connecting the 2 points in the space, right? If I have the points 2, 2 and 6, 6, the distance, the Euclidean distance between them is simply the length of this particular line that connects this point and this point, right? And the way you compute that length is by applying this formula, okay? You essentially take the difference between individual components and then square it, sum it, and then take a square root. Okay, so essentially the distance between these 2 points is 6 minus 2 square plus 6 minus 2 square and square root of the whole thing. Okay, that's the Euclidean distance that we already know from our school days, right? And in practice, so in this example, your data is only 2-dimensional. So you have x and y coordinate, okay? But in general, the data can have many dimensions, right? And therefore, each data point is represented by n-dimensional vector or a coordinate format. Okay, so here A1, A2, A3, An are n different dimensions of the same point. And in this example, n is equal to 2, and A1, A2 are 2 and 2. And B1, B2 are 6 and 6. Okay? So that's the way you represent your data points in an n-dimensional space. And n-dimension means n different features that are present in your data. Okay? Like if I want to represent my customer as amount of money that he spends in my store per every week, and the age of the customer, and the gender of the customer. Okay, if I have these 3 data attributes that I want to capture, then my n is equal to 3. Okay, because every data point that I collect will have these 3 values associated with them. Okay, so yeah, if I have n-dimensional data points, then my Euclidean distance is this. And the Manhattan distance is computed like this. Okay, it's simply the absolute difference between individual components, like A1 minus B1. Take the absolute value, and then you sum those absolute differences. Okay, and what you get is something called as a block distance. So Manhattan distance is also called as block distance. And if you are in US, or if you are familiar with what Manhattan is, the roads in Manhattan are strictly organized, or mostly organized into these squares, right, into blocks. And essentially, if you are in at a building here and you want to go to a building here, the route that you will follow is essentially different blocks that you traverse, right? You go from here to the next intersection, and from there you go to the another intersection, and then keep going. Okay, so this is like Chandigarh in India, which is the only planned city that we have, where all the roads are organized in a nice block structured manner. And what you get out of this particular equation is the number of blocks that you traverse in order to go from one point to the other point. And that's why it's called block distance as well as Manhattan distance. Okay? And in certain applications or for certain data, this Manhattan distance makes more sense than computing a Euclidean distance. So that totally depends on the application and the data. Okay? So there's no like a silver bullet or one size fits all kind of a distance. It really depends on what you're trying to do, what is the data, and what is the application. Okay? Any questions so far? And in practice, if you don't know what to do, you just simply apply Euclidean and see what you get. Okay? Okay. So this is another distance or similarity measure, cosine distance or cosine similarity, which kind of measures the angle between the 2 points. So here, the 2 points are A and B, x1, x2, or A1, A2, B1, B2, instead of x2, y2. And the distance, the cosine distance, is essentially driven by the angle between the two vectors. Okay? And so tomorrow or end of today, we will see this document clustering example, which is like the Google News that we talked about. In those scenarios, you will use cosine distance, okay, the angle between them. And Srinivas says, how do you know what you got is correct? So I just mentioned that if you don't know anything, you try bunch of measures and see the performance, right? And how do you know one is doing better than the other? That you typically do, that you typically evaluate by looking at the resulting clusters. So probably you can eyeball, I mean, if you can, you get some sample of data from each cluster and try to make sense whether those data points really should go into the same cluster or not. Okay? Because for any application, you already have some kind of idea how those clusters should look like, right? If it's a sales profile, if I'm doing market segmentation, then I know that, like for example, for a distance measure like cosine distance, if I apply it on my market segmentation data, and if in the resulting cluster, person who spends only on necessity items and the person who spends on high-end computer games, if both of them are put into the same cluster, then I try to question the result, right? So those are the things that you can kind of eyeball the data and figure it out. Or there are, as we'll see later on, there are certain quantitative measures that you can compute, and based on those measures, you can evaluate one cluster is better than the other cluster. Okay? And so these are common things, but you will also have similar equations for Tanimoto distance and many other distances as well. Like if you have string data, for example, you will not use something like these measures, but you will use something called as a Hamming distance or a edit distance. Depends on the data, your distance measure will also change. Okay? So now that you have these distance measure defined on your data, our next goal is to actually go ahead and do the grouping or clustering, right? Look at the data points. You already have the distance or similarity measure defined on those data points. Now your goal is to find the groupings, okay? And as we already said, the goal is to have a clustering arrangement such that you have high intra-cluster similarity. That means within the cluster, the points should be close to each other. in terms of the distance measure or the similarity measure that we just defined. And between the clusters, the similarity should be as low as possible. Or in other words, within the cluster, the distance should be small, and across the clusters, the distance should be large. Okay. Now, this is our goal, and let's see how do we get to that goal. Okay. And one algorithm that we'll see in this context is something called as k-means, which is the most popular one. And without this, you can think as you don't know what clustering is. Okay. So this is a fundamental technique. And this is example of clusters, which we already talked about in, we have seen many other examples. Like here, my data has only two dimensions. One is gross monthly income, and the other one is current balance of that particular customer. Okay. And I have many data points, and clearly there are, in this particular example, let's say there's one cluster here, one cluster here. Okay, and by looking at those clusters, I can kind of make some conclusions about those consumers. Like for example, this cluster, people in this particular cluster have high balance but low income. Okay, so that tells you something about their financial situation. Okay, and similarly, these are the guys who have high income and low balance. That means they keep spending a lot. Okay, and if you have, let's say, a new product for credit cards, depending on the semantics that you will derive from these clusters, you may be trying to target that particular credit card product to this cluster over this cluster. And similarly, if I have a loan product or some other product, I may be targeting this particular segment than this particular segment. Okay, that's a subsequent thing that you can do on top of this clustering. Okay, but the thing is that all the people in this particular cluster, the distance between them is very, very small. Okay, all of them have high balance and low income. And if I take 1 point from here, 1 point from here, the distance between them is typically large. Okay, and that's why they are put into two different clusters. Okay, and that's why there will be much differences between objects from cluster 1 and objects from cluster 2. Okay, and Gaurav says, what are the other clustering techniques? Which ones to use when? So after we discuss k-means, I'll show you other popular clustering algorithm, at least the names. And so that answers your first question of what are the other clustering techniques. We'll see what they are later. And to your second question, which is which one to use when, that's again, there's no clear answer to it. Again, there's no silver bullet, there's no one size fits all kind of a clustering technique. It always depends on the data and what you're trying to do. Okay, so yeah, there's no clear answer for it. And you will see this kind of question coming again and again for every class. Like when we look at classification algorithms as well, there are like 10 different classification methods that are available. Which one to apply when? Again, nobody knows. There's no clear answer. So you typically just try a bunch of algorithms and see which one gives you better performance. Again, that better performance, you can either quantify it or kind of see what those results are by eyeballing it. Okay, and Sudhir says, what are the features you use to get these clusters? So features are exactly the dimensions. And in this particular example, there are two dimensions or two features, which are the gross monthly income and current balance of the customers. So if you imagine the data, input data, it's essentially like a 2-column data where each row indicates a customer, and the first column indicates current balance, second column indicates gross monthly income. Okay. So in other words, I mean, just for the purpose of others as well, I'm using these terms interchangeably. Dimensions, features, or variables, or columns, all of them refer to these different attributes with which we are going to learn. Okay, and that's why in this particular case there are 2 dimensions, or 2 variables, or 2 features. Okay, all of them are the same thing. Make sense? Okay. So this is the algorithm that we are going to use in order to compute our clusters using k-means. Okay, and at the end of this slide you will realize why it's called k-means. Okay, and the first thing to understand here is the k. K is the number of clusters that you want to compute from the data. Okay, so this is the input to the algorithm. It's not something that algorithm finds, but it's something that you as a user should give it to the algorithm. Okay, so you will give 2 things to the algorithm. One is the data, actually 3 things. One is the data, other one is the distance measure. How do I compute this distance between the 2 data points? And the third one is the number of clusters that you want to compute. Okay, so given these 3 things, the algorithm will go ahead and find those many clusters from the data. Okay, and how does it find? Let's go through this flowchart and we'll understand what that is. Okay, so we have the number of clusters k, which is the input to the algorithm. The first thing that you do is select random k cluster centers. Okay, meaning randomly select k data points. Okay, and then so essentially, I mean, going back to this diagram, so I have data set like that, right? Bunch of points in the space. Okay, and I'm saying, let's say k is equal to 2. So I have all this data in a flat file, like a CSV file with XY coordinates, and I'm saying, okay, take this data, use Euclidean distance as the distance measure, and take k equal to 2, and give me the 2 clusters that are present in this particular data. Okay, so what we are going to do, first thing is I randomly choose, okay, let me change the color of my pen. So I am going to randomly choose k data points in my data, k points in the space, okay, which can be, let's say, here is 1 point and here is another point, okay, randomly. And I'm going to organize my clusters around these red points, which are called as cluster centers, okay. So also called as centroids. Okay. Now once I select these 2 red points, I'm going to compute the distance between every point, every data point, and the centroid that we chose. So I compute the distance between this black point and the 2 red points. And then I'll take another data point here, and I compute the distance between the both red points. And similarly, I take this data point and compute the distance between that and this point, and this data point and this red point. Okay, so I compute the distance between my data objects and the centroids. Okay. Now, what do I do with these distances? I essentially use these distances to assign my individual data points to the best cluster centroid that I can come up with. Okay, so that means I have, let me change my color again. I have this data point, okay, and I compute two distances between this one and the red point, this one and this red point. So I have distance D1 and I have distance D2, okay. Sorry for my bad writing, but I hope you can understand. So I compute two distances, D1, D2, and I choose whatever is the lowest one, okay. So let's say D1 is smaller than D2. Then I'll say this particular data point belongs to this particular cluster center. That makes sense, right? Because I'm assigning my data point to a cluster center which is closest to that data point, okay? And that's exactly what's done here. So you're grouping these data points based on the minimum distance. So you do that for this one black point, and you do the same thing for other black point, and you do the same thing for all the black points, okay? You're essentially computing the distance between my black points, which are your data points, distance between those data points and your cluster centers, and then you're assigning to the cluster center which has the closest distance, okay, or the smallest distance. So at the end of that, essentially I have for this red point, I have bunch of points associated with them, right? And similarly for this data point, I have another bunch of data points assigned to that, okay? So that kind of gives you one version of grouping, right? That's essentially what you're constructing. You're essentially randomly chose two red points, and then you're assigning all your black points to one of these red points, okay? And at the end of this, you get something like that, some clustering of your data points, which may be bad, but that is what you have at the first at the end of the first round, okay? Any questions so far? So Sajjad, are you okay with it, or? Okay, Dilip says, what happens if distance D1 and D2 are equal to both centroids? Then in that case, I'll randomly assign it to one of them. It doesn't matter. Okay, Srinivas says, what if the data point sizes are different? What do you mean data point sizes? Yes, I can unmute you. Go ahead, Srinivas.
Yes, when I meant data sizes, right? So for example, if you go back to your slide again. So in this case, let's assume you had 20 of them in the top one and then 40 of them in the second one.
That's fine. Doesn't matter.
So
we are essentially saying if I divide my data into clusters and one cluster is smaller and another cluster is larger, that's totally fine. Because there's no requirement in our problem statement which says the clusters have to be equal size, right? The only constraints that we have is within the cluster, the similarity should be high. Across the clusters, the similarity should be low. Those are the only constraints that we have.
Okay, then how can you balance this out? I mean,
okay, that's a different constraint that you're trying to bring in, right? The balance between the clusters. Why should I mean, balance need not be important for all the applications, right? Like for market segmentation, for example. What is the use of having balanced clusters? I can have one high-end customers who spends a lot, which may be very, very small compared to a segment which spends on necessity items, right? So one cluster is small and the other cluster is large. That's totally fine with me, right?
Okay.
You don't sound convinced.
I'm not able to relate it to some. It'll take some time, I guess, but I'm still getting
But
into
in this
the
example, do you see the requirement of having equal cluster sizes?
Probably not. Probably not. I mean, I'm still trying to correlate to the real application where I can apply things and then start this one. But I'll get there. No worries.
Okay. I mean, just hold on to that, and maybe it will clear once we
Sure.
Go a little further.
Yeah.
Okay.
All right. Thanks.
And okay, bunch of other questions. Let me. So Vivek says, how do I choose a centroid? We'll get there, but for now, just assume that these are two randomly chosen red points. Comes as part of stats package. So which is the base package. It will come automatically. You don't need to install any library for it. And all it takes is the data set, which is X. In this case, our data is the data set, and the number of centers, cluster centers that you want. Okay. And you can also say the max number of iterations. So we said that we repeat this process until the movement of the cluster centers is minimum, right? But instead I can also say, okay, run it for 10 iterations, and after that I'm okay, whatever I get. Even though cluster centers move after the 10th iteration, I don't care. I just want to run for 10 iterations. Okay, that's something you can specify, the number of iterations to run. Okay, and nstart is just random starting points. Okay, like one thing that I did not show here is this one. How do I find the optimal set? So we said we start randomly, right? And obviously, if you think about it, you will understand, which is if I start in very, very random places, I may get different results as well, right? So my starting point can affect the solution that I will get at the end. Okay? And obviously, to alleviate the problem, for any given data set, I try a bunch of random starting points. Okay, I take one starting point, do the clustering, get a solution, and then I randomly choose some other starting point, and then do the clustering, get the solution, and then get the better among all these solutions that we get. Okay, so that's what this is. If I say nstart equal to 10, I will choose 10 different starting points and then run 10 k-means algorithms and then choose the best among them. Okay? So that's the nstart. And similarly, there is some other algorithm which you don't need to worry about. And that's how you use that particular function. So in this particular case, when I say c equal to k-means of data comma 5, essentially I divided my this data set into 5 clusters, and the clusters are and you can see that arrangement here. So the first, second, third, fourth data points belong to the third cluster, fifth data point belong to the second cluster, and so on. Okay, so this is a final clustering arrangement of that particular data. But this is all internally doing all the iterations that we talked about. Okay, it did all these iterations again and again, and at some point it figured it needs to stop, and this is the result at that point. Okay, so this is just like a black box algorithm function that you call, you get the result. It doesn't really show how your cluster centers are moving. Okay, Vivek says we are trying to cluster based on what? And in this case, we are clustering based on the purchase profile. Like if customer 1 spends 12,000 rupees on fresh product and customer 3 also spends around 12,000 rupees on fresh products, then that means both of them are closer to each other and therefore they belong to the same cluster. Does that make sense, Vivek? So I'm clustering based on the profile of their purchase behavior. No, clusters will not be fresh milk and etc. Clusters will be, there's no name for the cluster. It's just that one cluster will have a bunch of people who spends in a similar manner. Okay, so let's say you and I spend 1,000 rupees every month on fresh products, and Anurag and Srinivas spends 2,000 rupees on fresh products. Then we both will be in one cluster. Srinivas and Vivek will be in the other. Srinivas and Anurag will be in the other cluster. Okay, so the meaning of our cluster is that our purchasing, our spending on fresh products, or cumulatively our spending on fresh milk, grocery, all of these are similar to each other between us. And between Srinivas and Anurag, their purchasing profile will be similar. Yes, so fresh milk, grocery, all these are the dimensions, or the features in your data, right? Okay, Anurag, it's obviously hard to plot it because it has multiple dimensions, right? So we need to, channel and region may not be meaningful. So if you remove these two features, for example, I'll have 1, 2, 3, 4, 5, 6 features. So I need a 6-dimensional space to plot it. So, okay, let me unmute Vivek. He wants to speak. Yes, go ahead, Vivek. Vivek, I unmuted you. Okay, somehow we cannot hear you, Vivek. Anurag, yes, there are 3D graphs, but there are only 3 dimensions, right? In this case, we have 6 dimensions. So I can still say plot of D, plot of data, but I get something like this. It's very hard to understand, right? It basically, so these are the dimensions: channel, region, fresh, milk, grocery, blah, blah, blah. And this is the plot between fresh products and milk. And this is a plot between milk and grocery. But this is hard to visualize than our previous thing. Okay, and Srinivas said number of iterations should take care of the final endpoint irrespective of the starting point. So your answer should be same irrespective of the starting point. Actually, no. That is because of something called as local minima and global minima. Meaning, I'll get to that point in the next class, Srinivas. Just remind me in the next class if I forget it. I'll explain why we don't end up with the same solution irrespective of the starting point. Gaurav says, where do I get the distortion value? And that you can get, so C is the result of k-means, right? And it has bunch of things. If you see structure of C, it has a cluster, which is a vector which tells you which data point belong to which cluster. Okay, and the actual centers, which are like our C1, C2, C3, C4. And these are the things that are the metrics. So within SS is within sum of squares, meaning the distortion that we computed. So if you remember here, distortion, it's called within sum of squares because you are computing the distance between the data point and the cluster center. So you are computing the distances within the cluster. So that is the metric here. Okay, this is within sum of square for the first cluster, second cluster, third cluster, fourth cluster, fifth cluster. So this distortion is simply the sum of all these values. Okay, so when you have better clustering, this values should be low, and the between SS, when we that means between clusters, this should be as high as possible, right? That's the goal of our clustering, right? Within the cluster, we need to reduce the distance. That means higher similarity. And between clusters, we need lower similarity. That means higher distance. So this should be high, this should be low. Okay, Anurag, let me unmute you. So any other questions about clustering in general? So, okay.
Hello, can you hear me?
One second, before you ask that question. Madhurendra says, how do we interpret the 5 clusters in this example? How will we associate these clusters with the amount spent? So that I can look by looking at the centers, for example, right? So here you can see that the center is kind of the representative, right, as we spoke. So the first center is saying that, okay, all the data points in this particular center, in this particular cluster, have values around 4,700 rupees spent on fresh products, 11,000 spent on milk, and so on. So these are kind of the representative data points for that particular cluster. Okay, and then based on this, you may give whatever name you want. Probably these are grocery friendly customers, these are fresh product friendly customers, and so on. Okay, does that make sense, Madhurendra? Okay, go ahead, Anurag. What's your question now?
Yeah, actually I have 2 questions. Very first is along the same line. As you see, we have a data, and you have with the k-means function, you have created the, like you have divided all the customers into different segments. But what's the best way to see that data? Because I was thinking the plot, but plot is not a proper way of doing it because we have multi-dimensions here. But we have a huge amount of data, so how can we just quickly understand like these 100 customers should, like they should go into this bucket, because we already bucketed it into the R with the help of one function. But what's the best way to see and quickly analyze it, the end result?
So that's why you have something called summary, right? Like we talked in the previous class. The summary just gives you high-level picture of the data. But I mean, I see a problem of how do I visualize or how do I see the data, and that's difficult. When you have larger dimensions, you cannot do that. And that's why in machine learning, it's typically called as cursive dimensionality. So as your dimensionality increases, your problems in terms of visualization, intuition, and all those things will go down. And that's why there's, and even worse, the algorithms will become intractable. They take more time to run, and it's hard to do any good learning. And that's why there's something called as cursive dimensionality. Okay, that's a known problem. And the typical way, if you have thousands of dimensions, you can imagine how the problem is, right? You don't even know which feature is better than the other. And you may be putting a lot of noise and you may screw up your results actually. Okay? And in those cases, there is something called as dimensionality reduction. Okay? What that says is, if I have 1,000 dimensions, and if I think, oh, this 1,000 dimensions is just too many and I might get distracted by all the noise present in this 1,000 dimensions, these kind of dimensionality reduction techniques will help you identify a smaller subset of dimensions which are kind of good enough for your analysis. Okay? So this 1,000 will become 5, 6 or 10 depending on the data. And then you can get only those 10 dimensions and focus on your analysis. Okay? So that's, I mean, yeah, that's dimensionality reduction techniques. And there are a bunch of algorithms in that class of techniques.
Okay, got it. Okay, and actually my other question is like, it's like a very basic question. I'm just wanted to understand what machine learning is, because I have a little bit of understanding Hadoop. So I'm just saying a statement, let me know is it correct or not. So machine learning is just, we can do it on any kind of data. It could be Hadoop or normal or any kind of data. And R is just a tool to do it. We can probably do it in Excel also and create some model, right? But R is just a tool to do it. But I'm saying if we attach machine learning to Hadoop through Mahout, that's like a complex way of doing it.
So, okay. Before I answer that question, you said something like, I can run machine learning on Hadoop as well.
Yeah, right? Not machine learning, I'm saying machine learning on Hadoop data, like a big data, it is done through Mahout. That's what I'm thinking.
Right. And what is your question about that?
No, I'm just saying, is it correct? My understanding is correct. That's what I was saying.
Yes, because, okay, what is Hadoop? It's just a mechanism in which you store the data, right? Just like we have Windows file system, we have Linux file system, we have some other distributed file system, we have Hadoop file system as well. So it's just a service which lets us store big data, right? Windows file system is not good for big data sets, but Hadoop file system is good for big data sets. So ultimately, it's just a file system.
Right.
And my data is sitting in one of these file systems. And what is Mahout? It's just a Java program which runs k-means. And it needs to access data. That means it needs to read the data from some file system. It can be Windows, it can be Linux file system, or it can be Hadoop file system. And if it is Hadoop file system, Mahout will work on top of it, because that program is written to read from Mahout files, Hadoop file system, right? So similarly, R, what is R? It's just a program that reads data from file system. In this case, I'm running on Windows, so it's reading from Windows file system, and it is doing the analysis and giving you the result. Now, whatever we'll see later on in the class, we can make R to read from Hadoop file system as well. Okay?
Right.
Just like, so R by default, it can read from Windows file system as well as Linux file system, depending on which version of the software you install. Okay? And with some extra packages, it can read from Hadoop file system, or it can read from databases, or it can read from, I don't know, some other things. Okay? So, so the point that I'm trying to make out is Hadoop, Linux, Windows, these are all just storage mechanisms.
Right.
That has nothing to do with data analysis. Whereas your Mahout, your R, your SAS, or your Weka, all these are different softwares which can read the data from somewhere. Each one has its own limitations, like R by default can only read from Windows and Linux, not from Hadoop. And Mahout can only read from Hadoop file system. And SAS can read from, I don't know, whatever are the storage adapters that they created, right? So these are the softwares which read data from somewhere and then do this analysis and then produce the result. And yeah, that's how I put R, Mahout and all these things at a higher level, and your storage things are at the lower level.
Right, right. Because sometimes, you know, if you're just able to connect all the different pieces together, so you can visualize it like how these pieces work together. Sometimes I think in that way. And just one more quick question then. R is like what people used to, like data science people or statistician used to use before R? What was the tool, or what was the tool they used for all those kind of
R is actually one of the first tools. As I mentioned, it was there for 30 years probably, 20 to 30 years.
Okay.
And before that, first of all, computer adoption itself was low. And actually before that, I mean, there were some tools, but those were all like COBOL, right? COBOL is there for so many days, which were primarily for doing computations and storing data and stuff like that. And even before that, they just worked on papers.
Okay.
Okay, and back then the data that they were analyzing is also like sociologists will survey like 20 people in the university and get the data and do some analysis on those 20 data points. Okay, so that's why a lot of techniques that are there in the statistics are with the assumption that the data is so small, and then how do you make good observations from those small little tiny data sets.
Right.
Okay.
I think this big data thing has changed everything currently.
Exactly.
Yeah, thanks a lot. I think that really helps.
Sure. Srinivas says there will be lots of questions as we work on examples. We do get to work on examples in class, yes. And there are some examples already on the LMS. Murali says he felt watching TV show called Numbers. Yeah, I know that thing, but this is making more sense. Good. I am glad to hear that. Any other questions, guys? Okay. So if no other questions, we'll stop here, and we'll resume in next class tomorrow. Gaurav, I can try to get some pointers tomorrow on dynamic pricing model. I mean, I may not be the bestest person on that particular topic because my exposure is limited, but I'll get whatever I can get. Okay. Okay, great. And before you go, please fill in the survey like you did last time, and we'll see each other tomorrow. Bye. Good night.